So we are talking about inverters. It's good that you gave me feedback about corrections. It's okay if you give me feedback because that is how I can, correct things, I can improve things. Of course, you have to also understand that sometimes may be wrong and then I would have to still not give you marks for that. I can try to convince you quite a lot, right? But sometimes you may still not be convinced, but I am convinced that you don't deserve a mark there and I would still deduct. You may still feel that, I deserved, I didn't get it. Such situations are unavoidable, right? Just to make you happy, I cannot give you marks wherever you think it's correct, right? And that's okay, that will happen. Of course, that should not lead to very drastic effect on your overall marks, but that would happen and then all of you should be mature enough to understand that this will happen. Only thing is you take it as a learning to try to understand the perspective of why the question was asked, where did I go wrong, and sometimes just you don't have to accept it also, you just register it in your mind, keep it in your mind, kahin park karke rakh do. Later on, you come back and you think that that is correct. I still remember one small thing. I was like very small at that time, maybe class 7, 8 or something. Jab mujhe zyada, I was not very good at math and other things, right? So there was this formula, not in class 8, maybe in class 9th or something. So a plus b whole square, right, is a square plus b square plus 2ab, and a minus b whole square is a square plus b square minus 2ab, right? So this formula was taught somewhere and I don't know why, but I was confused that a plus a minus b whole square should be a square minus b square minus 2ab. For some reason it was there in my mind. Now I don't recall, but it's still there in my mind. And then I was very strong कि यार यही सही है, कैसे गलत हो सकता है? And then of course I kept thinking, teacher ने तो mark नहीं दिया. But much later I realized कि नहीं है तो नहीं है सही. But what I'm saying is perfectly fine to register it in your mind that because you would learn a lot of other things from there later on. Okay, now coming back to the class, so let's discuss today about inverters, right? So inverters is, we have already seen a single phase inverter. If you ask me, in real life, a single phase inverter has a lot of applications, but still not as many applications as a 3-phase inverter. Where do you see a single phase inverter? Honestly, if you ask me, I don't think in this room anywhere we have a single phase inverter, right? We do use single phase inverter as a component for a DC to DC converter, where we convert a DC voltage into a high frequency AC and then use a transformer and then rectify, right? So let me give you that example. So using this could be as simple as that. You can have an inverter like this. This is the inverter which you have seen. You have a transformer here. So you invert DC voltage, let's say this is 400 volt. You invert it, you make a high frequency voltage across these two terminals, right? Let's say terminal, let me call it voltage V1. So you make a high frequency voltage V1, then you put it in a transformer either to step it up or step it down, and then you use a rectifier. Yeah, once you rectify it, this is where you will get the rectified voltage, which is another DC, right? So this, if you see, it's actually a DC to DC converter, right? It will have a name, which I am not telling you today, but it will have a name. So once we have only learned basic DC to DC, those also, if you recall, the flyback and the forward, in a way, directly or indirectly, were doing this operation of inverting the DC voltage, putting into a transformer and then rectifying. Right? This picture here is of course much more explicit than that, where you can clearly see that there is an inverter, there is a transformer and there is a rectifier, and then what you have is DC. There are multiple associated topologies with this one, with a lot of names and so on. Not getting into it, but just to give you one of the applications where you use an inverter. Right? This is the same edge bridge inverter. Then where else do you use inverter? Anyone, where do we use single phase inverter? In house UPS systems, right? If it's a small house UPS or an inverter, that would use a single phase inverter because your house mostly have single phase loads. And by now I think you do understand that why some of the houses, when power goes out, UPS turns in, you have that noise coming from the fan. Some of the other houses don't have that, right? I remember in that discussion also somebody said that in our house it doesn't happen when power goes away. Inverter operates but still fan operates, there is no problem of humming sound coming from the fan. Why is that? Why some houses have that humming sound from fan and others don't? Sorry? But why would, both are using single phase inverter, both are, let's say, using this kind of thing. One second. Both are using single phase inverter. There is a battery here, right? There is a battery here which is inverting, and then you may be using, if your battery voltage is 12 volt, it may not directly give you 12 to 30 volt AC, you may be using a step up transformer after this, right? But this is how most of the house, let's say, inverters would look like. So why is it that same inverter being used in some houses of some make, some company would make a humming noise out of your fan, the others would not? Yes, okay, that is fine, harmonics, but anything extra to that? Go ahead, I mean, harmonics is fine, but can someone elaborate a little bit more? So any, if the fan is oscillating, it's very simple that if it's only a sinusoidal current in the fan, then it will just produce a torque, average torque, which is rotating. If it's like vibrating, if it's oscillating, if sound is coming, means internally there's some vibration. That means there are other frequency component going into the fan which is creating this sound, right? What could be that? So if you see, if I use fundamental modulation here, right, as we understand, we have, if you use fundamental modulation, you will have a fundamental component 50 hertz, you would have a third harmonic component, you would have a fifth harmonic component. And if these guys goes into fan, these are sort of low frequencies, audible frequencies also. So you would hear third, fifth, seventh, you would lead to some vibrations, and you can hear it, those vibrations. So if you do fundamental modulation, then you would have that thing. But if you do sine triangle modulation, then what happens is these frequencies are not there. Your frequency goes to a very, very sort of far left value. In induction, it's an induction motor, it has an inductance. That inductance further attenuates those frequency, because as an inductor, it gives a minus 20 dB per decade of attenuation. So it's really far off in the left, provides large amount of attenuation, and hardly there is any high frequency current goes to the fan if you are using SPWM. So if you are using SPWM, what is SPWM stands for? Sine pulse width modulation. Then you would not actually hear those sound. But if you are using fundamental modulation, then you would hear those sound. Fundamental modulation means switching once every 50 hertz. So you have these low frequency components with you, right? So I mean, of course, generally implementing this is little bit cheaper than implementing this, right? For house use, maybe such sophisticated scheme is not required. So some manufacturers, some products would work with fundamental modulation, much easier to implement. Someone may have more sophisticated sine triangle pulse width modulated, and then in that case you won't of course feel much of a difference if you are running fan with it, right? That is true if you have a induction motor fan. Of course, if you have a BLDC fan, then it's completely different. So if you see a BLDC fan, how it would look like, it would have since BLDC fan requires an inverter, so first stage is a rectifier. It will have a, let's say, a full bridge rectifier coming from the AC, and then you would have a 3-phase inverter, and this would run the BLDC motor, right? This is how a BLDC fan would look like, right? Not a simple induction motor fan. So BLDC fan means there is a BLDC. BLDCs are mostly 3-phase BLDCs, and they require a certain pattern, right? This is something which we have also done one lecture in the previous course, right? So we have talked about what is the pattern required. So to produce that pattern, you use a 3-phase inverter. To produce the supply for the 3-phase inverter, you use a rectifier. So you have 230 volt AC coming in. First step is you rectify. If you are rectifying, right, there is not much difference if the supplied voltage is pure sinusoid or it's like a square wave. Get the point? So if this is what you are powering up, then it would not make much of a difference whether you use fundamental modulation or sine triangle modulation. Is that okay? There may be finer details, there may be finer differences, but broadly speaking, right, this fan, as long as you have a DC voltage of the desired volt value, right, the actual torque production happens because of the inverter, this inverter control, not the inverter which is supplying your house. This is the inverter, this is the rectifier, this is the capacitor which is housed in the BLDC fan itself, right. So above the fan there may be some circuitry which would include these components. The 230 volt which comes to the fan comes from the UPS system, let's say, which is installed. So if that UPS is giving square wave or sine wave here, that would not really change much in terms of the operation of this guy, which is primarily controlled because of the fan and a DC voltage. Is this part okay? And therefore, if your house have BLDC fan, you would probably not observe the difference anyways. Any doubt? So this shows you actually one of the application of three-phase inverter, right? We were struggling to find applications for single-phase inverter. There's one more application of single-phase inverter which is in solar grid feeding, solar inverters and all those things. Three-phase is of course much more popular. So if you see, this is your fan, BLDC fan. If you see your washing machines would again have a BLDC motor, a three-phase inverter controlling it. Your newer air conditioning system would again have an inverter and a motor controlling it, again a three-phase motor. Railways, if you see trains, right, this would typically have an induction motor, again controlled using a three-phase inverter. Lifts, if you see, again there is an induction motor controlled by a three-phase inverter, right. So three-phase inverter is certainly much more popular. The reason is simple, because three-phase system or three-phase motors is logically, much straightforward. If you have a single phase motor, inherently there is no rotating field, so a lot of problems. Three-phase motor, you have a nice rotating synchronous field, right? And therefore, three-phase inverters became popular because three-phase motors are popular. This is a very common, sort of circuit which you would see. For lifts also, you have a normal a single phase supply in this lift, let's say, right? Then first you would rectify it, produce a DC voltage, and then you would invert it to run the motor. Is that okay? If your supply is single phase, then you have a single phase rectifier. If your supply is three phase, you can have a three phase rectifier. This is, why do we do this way? Why don't we directly run the induction motor using the three phase that is available? You get the question? So you have a three phase supply available in this building. You have a lift that is there, right? Lift has an induction motor which is also three phase. I can directly use that three phase which is available to me to run that lift, right? I can do that, or I can first rectify it, produce a DC link voltage, and then invert it, and then use this inverted voltage to run the induction motor. In this case, of course, you use many components. You use a rectifier, you use some DC link capacitor, some inverter. You want to control everything. There's some microcontroller, a whole lot of circuits and cost goes into this. So which one would you do? Would you directly run an induction? If this is not a BLDC, if this is an induction motor, would you prefer to directly run it, or would you prefer to use power electronics? So let's say this is your source. You have three phase and you have a three phase induction motor, versus if you have a source which is three phase, then you rectify it, then you make a DC bus voltage, then you again invert it, three phase inversion, and then you have three things, wires coming out, and then you run induction motor. So would you prefer A or would you prefer B, and why? This could be your lift motor, this could be your some other appliance motor and so on. So which one would you prefer to do, A or B, and what is the reason? Lift, let's just talk about lift now. Fan is single phase motor, should they? Lift is a three phase motor for sure, because it's considerable power. So if you talk about lift, which one would you like to do? No, I mean, as a layman, do I need speed control? Why do I need speed control? Okay. So you have, all of you must have experienced this, right? There are certain lifts where you go in, you close the door and thunk, it starts, right? All the old lifts, if you see, they start like instantaneously with a jerky motion. And then there are these nice lifts, you get inside, you press a floor, 25 floor, and you don't even realize when it starts and when it stops at 25 and like door opens, right? You are at 25th floor. So wherever you need the smooth speed control or smooth torque control, you have to do this, because this guy would, as soon as it connects, it would just give you certain voltage applied to an induction motor, and the induction motor would of course respond to that sudden voltage applied. But here we can start slowly, we can do V by F control, we can slowly build up small voltage, slowly increase it to 230, because you can control the voltage that is going in the induction motor. So most of here you can do speed control, there is no speed control here, right? You saw the application for lift, right? And you know clearly there is an advantage in terms of the user experience, right? Is there any other advantage of using this? So this is, we call it direct line start, as the name itself is quite obvious, and this is speed control. By the way, to give you a hint, you have done an experiment on this last year. So you should be able to recall what were the advantages of second versus the first one. Do you remember you did an experiment where you have used a V by F drive in one part and you have used an auto transformer or a variac in the other part, which was the line start one, the auto transformer one, because it was suddenly applying the voltage, and the drive is what was giving you speed control. So here you have, the name suggests you have smooth speed control, or torque control. What else? Any other advantage that you recall? Okay, that is a good point. Why do you say so? Almost correct. Almost correct. What he is saying is that if you use speed control, you can go to higher speeds than what you can achieve here. So the maximum speed that you can do here is limited. You can go to speed beyond that. Anyone? He is correct. So anyone remembers why that can be done? Okay, by decreasing the flux. What was it called? What was it called? Constant power zone, field weakening zone, right? You guys recall this? This was torque versus speed. Oh, sorry, torque versus speed, right? This was your characteristics. Very similar to DC motor. So you are operating somewhere in this region, right? This is if you have a fixed voltage and frequency. But if you have a variable voltage and variable frequency, you can operate in this line, you can operate in this line, you can operate in this line, or you can go beyond this and you can operate. In this region, we keep the voltage as constant, but the frequency we keep increasing, right? And therefore it was called as field weakening. So you can go at speed beyond the speed at which you were limited because of the 50 hertz supply, because here you can have a fundamental of 60 hertz also, right? You can do 70 hertz also. So you can increase the speed. Good. So this is called as field weakening because you reduce the flux. Any other advantage of this thing? Go ahead, recall what you did in the experiment. You did something, there was one part of it where you did something which was not about measuring something, but it was about, directly getting a sense of something. You remember that part? There was one part where you were not seeing the oscilloscope or not seeing the meter, but you were yourself getting a feel of what is happening, right? What was that part? Starting torque, right? Starting torque. In this case, the starting torque is limited. If you do V by F, you can have a much higher starting torque, right? So high starting torque. And one more point. And if I have to give you the hint for this last point, there could be many more, but one major point. The air conditioners, the old air conditioners, whenever they turn on, what do you see in the room? They keep turning on and off, right? They sort of operate with a on-off duration, right? Otherwise, So if an oil conditioner in your house or in office or in lab or wherever, you would see it turns on, it will run for some time, of course the sound reduces, it turns off. Then again after some time again it will start, right? It will keep doing that. And then when that happens, what do you observe in the room? Apart from the sound, you observe that the lights or few other things would dim for small moment, right? You would see a dip in the light, or you would see, okay, one light starts flickering for some reason. So what happens is, if you do line start, then there is large amount of current that gets drawn, right? If you do smooth starts using speed control, the input current is always limited. Induction motor line start initially draws about 3 to 7 times the rated current. So that large current it draws, which is what creates the dip in the voltage in your house or in your room, and that leads to some fluctuations of light and so on, right? So this also, the speed control one has an advantage of low starting current. Okay, if you remember these things, it's good. If you don't remember it, at least before coming for the next class, please revise it, because I would be using this. So you revise these topics which I'll write you, which you have covered in the last courses, in the induction motor, which is the torque speed characteristics, tau max formula. You recall the equivalent circuit of induction motor. At least you try to revise these 3 topics before you come for the next class, right? It will not take you much time. Yeah. Yeah. So this part is sort of, it rectifies, you get a DC voltage. Then it's the inverter which does the speed control. And yeah. So what we'll do is, I'll give you some time. So today you can go back and revise, and we will discuss about the logic or the control for speed control in the next lecture. But today's lecture, what we'll do is, we'll try to just understand this hardware inverter block, right? So inverter itself, if you see, it's like some switches and it's a hardware block. Then there is some controller or the logic which a microcontroller is feeding it. That part we'll discuss in the next class, right? What is the logic? What is the how do you really control this? How do you really achieve it? But in today's class, let's just see what is that inverter made up of, what is it look like, how does it operate. We'll only see this part today, and next part we will, once you revise these 3 topics, we can see the whole control loop in more detail. Any questions so far? Okay, so let's look at 3-phase inverter. The inverter that we saw, single phase, we just extended to build our 3-phase inverter. This was your single phase inverter, or rather this half part was a half bridge single phase inverter. When now you have 2 phases, I'll put one more, you have 3 phases, right? So you can use this. Let's say this is A, B, C. So you have a 3-phase inverter, right? Think of it as a combination of 3 single phase half bridge inverters. If I redraw this DC side, you can visualize it much better. So this point is O, okay? So this was a half bridge inverter between AO, right? So you have 3 half bridge inverters, so you have a 3-phase inverter. You can number it anyways. There are some books where you would see a specific way of numbering. I think we can just say S1A, S2A, S1B, S2B, S1C, S2C, right? A, B, C corresponding to the 3 phases, A, B and C phase. So I am just dividing the 360 degrees of operation among 6, each of 60 degrees, right? So each of these is 60 degrees. So this is 60, this is 120, this is 180, and so on, and this is 360. Now if you only look at, just one phase, you only look at SA, don't look at SB or SC, only look at SA, right? You have a single phase inverter, you can do modulation, you can do fundamental modulation where you will turn on SA1 for some duration and SA2 for some duration, right? You can do that, or you can do a sine triangle modulation also, which is where you would turn on both of them at a very high frequency, right? And that on and off is determined by comparing a fundamental waveform with a carrier waveform. So you can do both ways, you can do fundamental modulation, you can do a sine triangle modulation. Let's see a little bit about fundamental modulation of this inverter, and then we will see the sine triangle modulation also probably today. So if I first look at the fundamental modulation, if I look at fundamental modulation, how does this looks like? So SA is on for 180 degrees, S1 is on for 180 degrees, so VAO is positive, and SA2 is on for another 180 degrees, so for the remaining duration VAO will be negative, right? If I say this is plus VDC by 2, this is also plus VDC by 2, the total is VDC. So VAO when SA1 is on is plus VDC by 2, and when SA2 is on is equals to minus VDC by 2, right? So I can draw the waveform VAO as this one. Yeah, it should look symmetric. Sorry, I think I should just redraw it. Give me 1 second, I'll just redraw it. I'm not changing anything, I'm just making it a little bit more symmetric. I think I didn't put the gaps more appropriately. Okay. Is this fine? This is how VAO would look like if I do fundamental modulation. That means I only turn on one switch in fundamental frequency. How would VBO look like? How would VBO look like? And that I need some other color chalk. What was your question? No, we are just drawing VAO. We don't know whether O is grounded or not. So VAO is just voltage between 2 points, and I will see how you connect load to this. I will show you that, right? But VAO is just the voltage VAO. I don't think that O is connected to ground or A is connected to ground or anything. It's just voltage difference between 2 points. This VAO voltage has a name. It's called as a pole voltage. It has a name. It's called as a pole voltage. So VAO is nothing but the pole voltage. Of course, it's pole voltage for A, pole voltage for B will be VBO, pole voltage for C will be VCO, right? These are pole voltages. The name is pole voltage. Why it's called pole voltage, I don't know. It's called as pole voltage. From there, we will try to derive further once we get the colored chalk. Okay, let me try to draw VBO till he comes. So, how do you think VBO would look like? If you are doing fundamental modulation, you want to have phase difference between the 3 phases of 120 degrees, right? So VAO will be at a certain phase, VBO will be lagging 120 degrees, VCO would be lagging 240 degrees, right? So if this is VAO, how would VBO look like? It's lagging, so it starts from 120, it goes up, and then I'm just drawing a little bit below so that you can see the difference. Right, this is how, if this is VAO, this is VBO. Is that okay? It's lagging by 120 degrees, that means it's same thing is happening to VBO, only thing is after 120 degrees, right? It's going up after 120 degrees, going down after 120 degrees. Is that okay? Similarly, you can draw VCO, which would be further lagging the B phase voltage by another 120 degrees. How would VAB would look like? VAB would be VAO minus VBO, correct? VAB will be VAO minus VBO. So what would VAB be for each sector? We can see for the first sector VAB is plus VDCT by 2 minus VDC by 2, so it is VDC, okay. Let me not draw it as tall, we will probably not have much space, but this is VDC. In the second sector remains the same, in the third sector it becomes 0, fourth sector it becomes minus VDC and it remains like this and again becomes equals to 0. This is how the voltage VAB would look like. Right? If VAO we were calling as pole voltage, VAB we will call it as a, what do you want to call VAB? Line to line voltage, right? This is line to line voltage or just the line voltage, right? Whichever way. You can call it line to line or you can just call it line voltage is your VAB. So if this was VAB, you can imagine how would VBC look like. So VBC would be, you can draw VAB, you can draw VC, then you can subtract. If this is VAB, VBC would be same shape but lagging VAB by 120 degrees, right? So VAB is this, so VBC would be something like this. Right? And if this is VBC, if this was VAB. And you can similarly extend, you can draw the third waveform as well. Okay, now the question comes that what do you do with these three terminals, right? So you can have, let's take off an induction motor load for example, right? Induction motor load means you have an R and L, let's say RL kind of load, if I assume induction motor to be RL kind of a load, then I have this R and L connected. And if you have a star connected induction motor load, this is what would look like. So this would be your load. Correct? This is how you would connect a induction motor load to an inverter. What is this system? This is a 3-wire system because you have only 3 wires connecting between the source and the load. You can have a 4-wire system where you can use this middle point as O and you can connect it to this midpoint, right? You can have a 3-wire system, you have a 4-wire system. This again 3-wire, 4-wire we have studied in the 114 course, right? 3-wire means your source and loads are only connected through 3 wires ABC. 4th wire means you also connected through a neutral wire, right? You can operate this motor both ways. Let's first see what happens if it's a 3-wire case. So there is no 4th wire for now and we will introduce the 4th wire a bit later, but if you are not using the 4th wire, there is only 3-wire, right? So if it's only 3-wire load, which is what usually happens, usually motors are connected only through 3 wires, then you can, although this point is not accessible to you, you can have, this is your neutral point, right? And you can define the phase voltage VAN and you call VAN as the phase voltage. So you have 3 voltages here, you have a pole voltage, you have a line to line voltage or a line voltage and you have a phase voltage, right? How will you find VAN now? We have derived already, we have seen starting from VAO, we could find VAB which is the line voltage. Now how do we find the phase voltage which is VAN? Anyone, how do we find the phase voltage? Can you write something similar to this so that you can derive the phase voltage quickly? So VAN, how do we find? I can write this as, let's say, VAO minus VNO, right? I can write this as VAO minus VNO. VAO I already know, VAO I know. Do I know VNO? No. Coincidence? No. So how do we find VNO now? Can you try writing KVL equation, finding relationship between VNO by writing equations for all the three branches. So if I write equation for the first branch, I can say that I start from VO, then I add VAO, I will get the potential of A, subtract IA into RA, subtract LA into DIA by DT will give me VN. Can I write this equation for the first branch? Just cross check if this is correct. I am just writing the Kirchhoff's voltage law for the first branch. Starting from point O, I am reaching to point N. Is this okay? Now you write the three equations for B as well as for C. They will be same equations, just replace A with B and B with C, right? And then you add the three equations together. So this is one equation. Let's say this is equation number 1. Similarly, you write equation 2 for B phase, you write equation 3 for the 3 phase, and then you add the three equations. And that should be able to give you the relationship between VO and N, or in other words V and O. How will you get it? So if this was A phase equation, B equation will also have the same coefficients, only B. Assuming it's a balanced load, RA is equals to RB is equals to RC, and similarly LA is equals to LB is equals to LC. So if you add the three terms together, let me do it on the other board. If you add the three equations together, you would have 3 times VO plus VAO plus VBO plus VCO minus R times sigma of IA, right? IA plus IB plus IC minus LA times d by dt, or L times d by dt of sigma of IA is equals to 3 times Vn, right? If you add the three equations, you would get this expression. Is this visible at the back? Visible? Okay. 3 VAO plus VBO plus VCO minus R times the sum of 3 current minus L times d by dt of sum of 3 currents equal to 3 VN. Is it okay so far? What is the sum of 3 currents? Sum of 3 current is 0. Why is it 0? KCL, yeah. That if it's only 3 wire, there is no 4th wire, then sum of the 3 current must be equal to 0. So therefore, your this terms becomes equals to 0, your this terms becomes equals to 0. So what you are left with is VNO is equals to 1/3 of sigma of VAO. When I say sigma, it means VO plus VBO plus VCO, right? Where I goes to A, comma B, comma C, VIO. Is that fine? So you have an VNO also now, and you can use that, and now you can draw what is going to be VAN, right? You want to draw it? Let's draw it. Let's, for the first 60 degrees, what is VAO? VAO is VDC by 2. What is VNO for the first 60 degrees? What is VNO for the first 60 degrees? It will be VAO plus VBO plus VCO divided by 3, right? So VAO is positive, VBO is negative. What about VCO? VCO will be like this. Oops, sorry. Arey yaar, it's much easier to work on computer. You don't know how to undo it now. I have to redraw it now. Give me 1 second, I'll redraw it. There's no undo option to redraw it now. So this was VAO, this was VBO, yeah, so VCO is going up here and then going like this, and yeah, correct. Go up from here, it will continue like this, and then it will be for 1, 2, 3, it will be like this, and then go up here. Finally, this is VCO. Is it visible? Looks really bad. It's just 120 degree shift. Oh, sorry, 120 degree shift shifted from VBO. Right. So if you see now from 0 to 60 degrees, VAO is positive VDC by 2, VBO is negative VDC by 2, VCO is positive VDC by 2. So if you add the 3, you will get VDC by 2. Divided by 3, you will get VDCT by 2 by 6, VDC by 6. So VNO value is VDC by 6 for the first 60 degrees, VAO is VDC by 2. So if you do VDC by 2 minus VDC by 6, what do you get? 2 VDC by 3. VDC by 2 minus VDC by 6 is how much? 2 VDC by 3. VDC by 2 minus VDC by 6. VDC by 3. For the next 60 degrees, your VNO will be minus VDC by 6, your VO still remains VDC by 2, so you do VDC by 2 plus VDC by 6, how much is that? 2 VDC by 3, 2 VDC by 3, and then you can keep doing it and you should get something like this, is my guess, but you should go back and you should try to draw it yourself. This is how your phase voltage would look like. Okay, this is how the phase voltage would look like if it's a 3-wire balanced load, right? If it's a 4-wire system, how would the phase voltage look like? If it's a 4-wire system, how would the phase voltage look like? If it's 4-wire, if you connect this O point to the neutral, how would the phase voltage look like? How would the phase voltage look like if it's a 4-wire system? Yeah, VNO becomes 0, so phase voltage looks like same as pole voltage, right? So if it's a 4-wire system, you know, this is not true. You would not have the phase voltage as this, you would have the phase voltage same as the pole voltage. So this is for 4-wire, oh sorry, this is for 3-wire, and for 4-wire you have phase voltage is equals to pole voltage. Yeah, with the unbalanced load you would not have this voltage, you would have, you know, differences in the magnitude of these voltages. Usually we consider, you know, if you have a single induction motor load, we consider it's a balanced load, right? Because it's symmetric. Whatever happens to A phase, same thing happens to B phase, same thing happens. You have same number of turns, you have same core. So I mean, of course, nothing is ideal or perfect, but we do consider it as symmetric load when we talk about a single phase, a single 3-phase load. But if you have distributed loads, then you may have, you know, unbalanced loading. For example, between A phase and B phase you connect some load, between B phase and C phase you connect some other load, then there will be unbalanced, and then this voltage will no longer be true, you will change it, and you can, if you know the load you can derive it, if you don't know the load you won't be able to derive it, right. But you can still, your line to line voltages will remain the same, right. So you would still know what is the voltage applied across line to that load, you would not know the phase voltage in that case. Okay, now this was about fundamental modulation, right, which used to be, again quite popular, but I don't think people use it these days, right. Why we are looking at it is because this gives rise to the next one, which is using the sine PWM for 3-phase inverter, right. So if you have to do sine PWM, then what would you do? You guys have made this graph, can I erase it now? If you are doing sine triangle modulation, right, or in short SPWM, which we have studied how it is done, you have a carrier wave which is a fundamental wave 50 hertz, and you have a triangle wave which is, you have a modulating wave which is the sinusoidal wave, and then you compare it with the carrier which is a triangle wave, right, and then you generate the switch on and off signals using that, right. This was the sine triangle modulation. If I use that, then how would VAO look like? VAO will be essentially a trail of pulses, right. If you just look at that way, it would look something like, something like that. It will keep happening this way, this way, this way, this way. You cannot make out much from this waveform, right. But then if you put some sort of a filter, and if you see only the fundamental component in this, right, if you put filter, if you do averaging of VAO over a switching cycle, right, that means you are only seeing what is the average over each switching period. What you would see a sinusoidal waveforms, right, and this sinusoidal waveform would be nothing but M times VDC times sine of VDC by 2 in this case, because this is half bridge, M times VDC by 2 times sine omega t. If you remember in H bridge, this expression came out to be M times VDC times sine omega t, where M we call it as a modulation index whose value is between 0 and 1. So this is all sort of recap. If you recall the last lecture, this is what we discussed in that lecture. Any questions so far? Any doubt? Any question? VAN. Oh, the previous one was the fundamental modulation. You have doubt there? Now I have erased it. So we can talk looking at your notes after the class. So sorry, that's the reason I thought if you should, if you had any question before, that's the reason I asked you. But we can discuss it after the class. But is this part okay? Anyone has any doubt here? Okay, if there are no doubts, let me see if you really understood it or not. Last, फिर पीछे. What is this waveform? What is this waveform? Okay. Okay. What is this waveform? What is this waveform? Next one. Next one. चल तेरी बारी आई गई. Next one. Next one. क्या कर रहे हो यार? What is this waveform? Average over. Average should be 0, na? VO is a sine waveform, so average should be 0. How can this is not 0? No, you are correct. This is average of VAO, but average must be 0 because sine wave, if you take an average, should come out to be 0, right? Next one. No, there are so many square waves kind of thing there. But then the average of, if you take average of everything, it should be 0. So why it is not 0? Next person. next person, next person, next person. Why it is not 0? Pull. नहीं तेरा chance चला गया अभी. Next person, next person, next person, next person, next person, next person, next one. Why it is not 0? Say again. Yeah, so we are taking average over which interval in this case? We are taking average over which interval in this case? Which interval? Which interval? Carrier frequency. Good. Finally, right? So if I show you a recap, you remember we had this type of carrier, then we have this type of waveform, then this is where the comparison was happening, and the waveform generated across the pole voltage was this, right? And we are taking average over TS, right? What is the meaning of taking this average over TS? Why are we taking this average over TS? Is because this waveform is actually square wave. If you do the FFT of that, or if you do the spectrum of that, you will get something at fundamental, and then you will get some things around FS frequencies, right? There is nothing in between. So by taking an average over Fs, in a way I am trying to say that I am rejecting all of these guys and I am only keeping this guy. So I get a clear picture of what is the fundamental component in this waveform. Is that okay? The actual VAO does not look like this, right? It looks like a trail of pulses which you cannot really make out much information from there. If I average it over TS, each switching period, then in a way I am rejecting all of these higher frequency components, because averaging is like a low pass filter, right? So I am rejecting all of these components, I am only keeping the fundamental component. So I am just able to visualize how the fundamental looks like, and this is how the fundamental looks like. Of course, if I take the average over fundamental, then I am also rejecting the fundamental component, then you would see a, just a straight line, a 0. Is that okay? Not okay? Now is it fine? Sure? Okay, retest. Why is it not 0? अरे यार ऐसे मत करो यार. Anyways, fine. Okay. Any doubt so far? So if you do sine triangle modulation, of course you get this as VAO averaged over TS. What will be VAB averaged over TS? What will be VAB averaged over TS? If this is VAO, VBO will be 120 degree phase shifted. Why will it phase shift? Because this sinusoidal waveform, which was m sin omega t, instead of m sin omega t, I will consider now as m sin of omega t minus 120 degrees, right? So my B phase will be 120 degree phase shifted. So B phase will be 120 degree phase shifted. So what will be VAB look like? This we have done long back. You remember this was phasor VA, this was phasor VB, this was phasor VC. If you do VAB, you get this phasor VAB, which is 30 degrees leading VA, and in terms of magnitude it is root 3 times. So similarly VAB will be root 3 times m VDC by 2 sine of omega t plus 30. 30 degrees leading the A phase voltage and magnitude is root 3 times, right? You can draw it also, but this is how the expression would look like. This is again averaged over TS. Without averaging, it will just look like a trail of pulses, which does not have much meaning. Is that fine? Similarly, now you want to find the phase voltage, you can find the phase voltages as well, averaged over TS period, right? Because why we are doing averaging over TS period is because we know that, although the voltage has higher frequencies, but the current eventually that would flow because of the inductor, which will act as a low pass filter, it would remove the high frequencies, right? So we are looking at only the average period over TS. You can see both waveforms. If you go back, you can Google it, or you can see it in the notebooks. You will see you can see both waveforms. Any questions so far? Okay, then last question from my side. what would be the phase voltage in sine triangle modulation? What would be the fundamental component of the phase voltage in sine triangle modulation? What would be the fundamental component of the phase voltage in sine triangle modulation? Is this question clear? Question is, what would be the phase and magnitude of fundamental component in phase voltage in a 3-wire system? What would be the phase and the magnitude of fundamental component in phase voltage in a 3-wire system? For you to answer is, you need to just understand first of all the terminology. 3-wire you know, phase voltage you know. Phase voltage means I am talking about VAN, right? You know the fundamental component means where you are averaging over TS, right? That is the part which is the fundamental component, because we have removed the high frequency component. You know what is the phase means, you can either tell it in RMS, usually we expect to tell you in RMS, but and magnitude, sorry, the magnitude is in RMS, the phase is in angle theta, right? So where were we? Who answered the last question? Who was the one to answer the last question? Okay, next person, go ahead. You want to answer this? So you remember this thing would still be valid, you can still derive it, it will still be valid. Now can you answer this question? This would still be valid, right? VNO would still be 1/3 of sigma of all the three, because you can still write the same KVL equation which used to be here, we raise it, you still can add, still your summation of A currents will come out to be 0, it is a 3-wire system, you will still get the same equation, right? So what would this be? What would be VNO equal to in this case? The fundamental component of VNO will be equal to, what is summation of VAB averaged over TS plus VBC averaged over TS plus VCA averaged over TS. VAB is this, VAO, VBO, VCO. VAO is this, VBO will be phase shifted, VCO will be another 120 degree phase shifted. If you add the 3, what will you get? 0. Sine of omega t plus sine of omega t minus 120 plus sine of omega t minus 240. So this is 0, right? This is 0. So that means what you will get here? You will get same as the pole voltage, right? So your answer for this is same as pole voltage. Is that okay? So in sine triangle modulation also you can figure out, you would have the same magnitude and the same phase as that of the pole voltage, fundamental component. Okay, I think let's stop now.